Hey guys, today I'm doing solutions for round 673. And I did this round officially but didn't do a screencast because I want to take Div 1 rounds seriously. And I mean, I'll do screencasts for everything else, but I feel like Div 1 rounds is going to be lower quality just because I'm going to be very, very focused and not offering much commentary. So I prefer to only do screencast rounds where I'll actually be able to kind of do commentary and be helpful instead of just watching me stare at a screen and type for 2 hours. But if that's what you want to see, I guess you can let me know. But for now, I don't think it's going to be helpful. So I'll keep Div 1 rounds to solution videos, and everything else I'll just keep doing screencasts for. That is generally what I've been doing. Okay, anyway, we're doing solutions here. I'm going to kind of skip the statements because they're here. You can probably read them. The statements aren't bad, so they should be clear. So basically you have this array and you want to add some element to some other element like a minimum number of times. So let's see what happens in a single operation. For example, we have the bound of k equals 5. K equals 5, and we have 1, 2, 3. So if we add this element to some other element, then we add 2 to the total sum. But if we instead add this element to both of these, then we add a strictly lower value to the total sum. So essentially, it's always good to be adding the lowest element, because if we add a higher element, it's just going to mean we have fewer operations to do. So first, what you can do is you can identify the lowest element. Easiest way to do this is to sort the array, as it's already done. And then you can just see how many times you can apply this operation to all of the other elements using this one as the value that you add. This one is AI. And the formula for that is k minus AI divided by a of 1, the first element, and then that should be floored because you can't do a fraction of an operation. And then because of this, you can't apply any more operations to this, so this is going to remain unchanged. And because if you could, that would mean that there's some j such that aj plus a0 is less than or equal to k. But if that's the case, then you would be able to add a0 to aj. And so you would have done that instead. And therefore, there's no reason to worry about this number we're not going to do any operations on. Okay, that is A. Let's do B. It's a terrible letter. Yeah. So for B, let's kind of look at this function. Say k equals 7, and we have the array of 1, 2, 3, 4, 5, 6. Now, if we have some x in one array, what's going to make it contribute to the value of this f? That is, what do we not want to happen? If x is in a pair that sums to k, like there's some y such that x plus y is equal to k, then we can solve for this and we can say y equals k minus x. So x will only pair with elements that are exactly equal to k minus x. And if we put these values in different arrays, then there won't be any pairs. So we can put these values in different arrays for all values of x except for when x is exactly equal to k over 2. Then 2x equals k, and k minus x is equal to x. So that is a problem because we can't put different x's in different arrays. So what we want to do instead for these values of x is, if we put, say we put x1 values of x in the first array and x2 in the second, then we get the number of pairs of x1s, which is this formula. And this is a well-known formula, basically n choose 2. We get this many, which is equivalent to x1 squared minus x1 plus x2 squared minus x2 over 2. And so these values are just n because it's the number of x's, and that value is constant no matter what. So we can kind of get rid of this because we're trying to minimize this, and these values are going to be irrelevant. So now we're just trying to minimize x1 squared plus x2 squared over 2. But we can also get rid of the over 2 because that's constant. And the best way to do this is to make these values as close as possible. Kind of like mathematical intuition. So what we want to do is, if we have cx values of x, then we want to make them as close as possible. So we can make x1, say, equal to floor of cx over 2, and then x2 equal to the ceiling of cx over 2, and this will sum to cx in total. So essentially, if there's an x such that x is equal to exactly k over 2, which also means k has to be even, then we'll put the first floor cx over 2, or ceiling, doesn't matter, values of x in the first array, and then the rest of them will go to the second array. And as for the other elements, we just need to make sure that we don't put x and k minus x in the same array. And the way we can do that is for all x less than or equal to k over 2, or less than k over 2, we can put them in the first array, and then for all the remaining ones, we can put them in the second. This just works because, well, either, like, the minimum of these two values is either exactly equal to k over 2, which is a special case, or it's less than k over 2. And so we just consider the one that's less than k over 2, and we put those in the first array. And the other k minus x has to be greater than k over 2, therefore. And so we can just put those in the second array. So that's kind of the implementation. We just go through, first count the number of x's if such an x exists, and then just put the first of these amount into the first and then the second, or 0 and 1. Doesn't matter what the numbers are. And then for the rest of them, if x is less than k over 2, we put it in the first array, and otherwise we put it in the second. And this will minimize it because the only thing we really have to minimize is this value, and that we can do by having values like these. Because everything else will contribute 0 to the number of pairs that sum to k. Okay, now we have C, and this is where we get into the div 1 problems. So what has to happen? Let's focus on some number. Let's say 5, and let's say we have an array like this. So we have 5, and then some other number that doesn't matter, and then 5, and then 5, and then 5, and then another number that doesn't matter, and then 5. At what point is 5 going to be contained in all subarrays of length k? And therefore, for all subarrays of length greater than k. So first of all, if we can notice that if all subarrays of length k contain 5, then all subarrays of length k plus 1 also contain 5. Because if we consider all subarrays of length 3, like written out like this, then all subarrays of length 4 are just going to extend these by one element. And all of these already have 5, and this one gets gone. And all of these already have 5, so they're not going to stop having 5. And therefore, if it holds for k, it'll hold for all numbers greater than k. So now we just need to find at what point do all subarrays of length k contain 5. And we can do this by kind of looking at the gaps between numbers. Instead of trying to compute it like kind of naively, we'll say the biggest subarray that doesn't contain a 5 is this. is this gap between the two 5s. And we can also kind of put two virtual 5s on the end because the subarrays have to be at the ends. Or the subarrays can't go out of bounds. So implementation-wise, we can put two virtual 5s at the beginning and the end of the array, and we can do that for all numbers, and then it'll help us with implementation. So the biggest subarray that doesn't contain a 5 is in one of these gaps. It's in one of these gaps where there aren't any 5s. And as soon as we get to a size bigger than the biggest subarray, like by definition, all subarrays have to contain 5. Because otherwise it wouldn't be the biggest subarray. So all we need to do is we need to check all of these gaps between the 5s, and then we can see which one is the biggest gap. And then that will tell us the highest k such that all subarrays of length k don't contain 5. And we can do this for all numbers, kind of just by, like, we can store something like a vector of, not a vector, just like a list of indices for each value. For example, we'll put all indices that have 1. So in this sample where there's 1, 3, 1, 5, 3, 1, all indices that contain 1 are 1, 3, and 6. All indices that contain 2 are nothing. 3 is 2 and 5. 4 is nothing, and 5 is 4. And then again, we can kind of put these, we can put 0 and n plus 1 at the end, and that will basically simulate putting numbers at the ends of the array. Because again, any gap can't go out of bounds, so we can treat it like if a gap goes out of bounds, let's say for example here, then it will have to contain one of these 5s, and so we won't let gaps go out of bounds by doing that. So we can put all these virtual numbers in, 0, comma, n plus 1. And then once we do this, the answer for 1 is the biggest gap between any two 1s, which in this case is 3. The biggest gap for 2s is 7, if n plus 1 is 7, which it is. For this, the biggest gap is, once again, 3. For this, the biggest gap is 7. And for this, the biggest gap is 4. So now what do we know? We know that all subarrays of length greater than 3, so all subarrays of length greater than or equal to 4 have 1s. All subarrays of length greater than or equal to 7 have 2s. All subarrays of length greater than or equal to 3 have 3s, and so on. So what we can do is make an array where, like, basically, all right, this should be 4, my mistake. Yeah, greater than or equal to 4. So we can make an array that basically says, like, we'll put, for example, this represents all subarrays of length 4. This represents all subarrays of length 3, etc. And then we can say at 4, once we get to 4, all subarrays can have the minimum element of 1. And once we get to 4, all subarrays can also have the minimum element of 3, and then this can be like 5, for example. And so then we can basically do a sweep line along, and then we can take the prefix maximum of all of these values. And then that's just going to work, because the prefix maximum of, for example, 4 means that we're considering the maximum over all, like, constraints that say when we have greater than or equal to this number, we can have this. That's kind of a sketchy explanation, but basically, once we have this number, when we say anything greater than or equal to 4 can be 3, then anything on this range can be 3. So all of these 3 numbers are going to include 4 in their prefix maximums, and therefore, Like it's going to simulate taking the maximum of all of these kind of constraints. So we set up these arrays. So we set up this array, and then we get the minimum element for all of these values. And 1 is the minimum for 4. Even though we also have 3, we only care about 1 because that's the minimum. And then the answer for 1 is the prefix maximum of the first 1 elements. The answer for 2 is the prefix maximum of the first 2. Answer for 3 is that. Answer for 4 is that. Answer for 5 is that, and so on. And if there's no element in the maximum at all, then it's -1 because there's no value that is contained in all subarrays of length k. So for example, this answer will be 1, and even though we can get a 5 here, 1's better. So this is, I just said maximum, I just realized. I just said maximum this whole time, but it should be minimum because that's what we're looking for. Sorry, my bad. It should be minimum, not maximum, just to emphasize that. And we take a prefix minimum, so we have 5 here, but 1 is already better than 5, so we just keep the 1. Here we have nothing, so we still have the 1. And that's, for example, how we get the answer for this case. Although even this is slightly different because this gap is of size 3. I guess what we actually want is that the subarray is of length 2. So these would actually be like 1 less, but you can, yeah, you can kind of work out the math on that. It's just the size, it's the difference between the elements, that -1, because we're interested in this gap size specifically. So that's kind of it. We take prefix maximums. We say that all subarrays greater than or equal to 3 have 1s, so we can put 1s here, and then we just take a prefix maximum because any element after this, including that, will also be affected. So prefix minimum is what we want. God, I keep saying that. I don't know why. Okay, anyway. Yeah, that's how we do C. Now we're on to D. I'm basically just going to describe the strategy for how we do D. So the first step in noticing that, is that we want all elements to be equal. And in one move, we can subtract I times x from some value, and then we can add I times x to some other value. But in doing so, the sum of the array still remains the same. It doesn't change. And therefore, if we can't split the sum of the array into n equal elements, then automatically we can't do it. So let's say the sum of the array is s, then s must be divisible by n, or s mod n must be equal to 0. That's the condition. That's the condition for it to be possible. Otherwise, it's impossible. Okay, now why is it always possible if we can split the sum? Because there's a strategy we can make. And this strategy is essentially, we can kind of go backwards into doing this. If we could, one cool thing we can think about is if we can get everything, like the entire sum of the array, into the first element, then we could distribute s over n to all of these other values equally, because if we choose I equals 1, we can subtract any multiple of 1 from this, and we can add that multiple of 1 to this, and everything is a multiple of 1. So we can basically just distribute anything we want along the array as long as this value has the whole sum at the, before we do this. So somehow we want to make it so we have all of the the whole sum of the array in the first element. How do we make that happen? well, we can kind of go through, and what we want is we want all of these values to kind of give their sum to this. And now we have to figure out how to do that. Because let's say we have an array like 1, 1, 2, 3, 4, and therefore the indices are 1, 2, 3, 4, 5. Well, we can't actually make this happen. Like, we can't do any operations with I equals any of these. We have to first give some of this away, and then eventually we'll kind of get it back. And on top of all that, we have to do it in, this is n-1 operations, so we only have like 2n plus 2 operations left. And somehow we have to do everything using only that. We can also think of it as essentially every element only gets 2 operations. And we have to make it so all of these numbers give their whole value to this in 2 operations each. And the way we do that is we abuse the constraints. The constraints say all numbers have to be positive. That is strictly greater than 0. And that's important. Why? Because the strategy for making each element, the strategy for making AI give all their sum to A1 is as follows. First, we make AI divisible by I. So AI mod I must be 0. And then once we do that, then its sum will be a multiple of I, so we can use the operation to give the entire thing to the first element. So now, in only a single operation, we have to make AI mod I equals 0. Okay, now, the strategy to do this is, well, we can only give things from the first element. So consider the quantity I minus AI mod I. We have to give from the first element that much to increase AI to, actually it's more like, actually no, negative numbers are confusing, so we'll just do this. We have to give I minus AI mod I, we have to like increase AI by that to make it mod I equal to 0, because like AI plus I minus AI mod I, all that mod I should be equal to 0, and clearly I mod I is equal to 0, so we can get rid of that. Then we get AI minus AI mod I is equal to 0, and then we just get 0 equals 0. So that works. So now we have to be able to we just have to be able to add this quantity to all of these numbers. And the way we do that is, well, first what we do is we can like observe a few things about this number. First of all, because if this is 0, then we end up, this whole quantity is I. And so, like, that's bad because I mod I is equal to 0. So we don't have to add an extra additional I for that. So what we can instead do is add this quantity I minus AI mod I, additionally mod I. And that makes it so we don't accidentally add something we don't need to. So because this is mod I, this whole quantity is less than or equal to I minus 1. This is important because all elements are positive once again. So every time we give some of these numbers to A1, we increase A1 by at least 1. So A1 can, in the worst case, start at 1. And then by A2, we get it to 2. And then by A3, we can get it to 3, and so on. And the important part is that at every step, because all numbers are positive, A1 is greater than or equal to the value I minus 1. Which means that because this value is less than or equal to I minus 1, we always have enough of A1 to give this value to the next element. And that's good because elements can't be negative after an operation. So this makes it work for that. So the strategy, to recap, is at the end of it, we have to make all of the sum be in the first element. And then the way we do that is we can go through the array in like increasing order. And we first give just enough to make this divisible by this, which, as I just showed, we can always do. And then, because this is now divisible by this, we can give the entirety of this value to the first element. And then we move on and do that for all of them. And this takes 2 operations each, so this ends up using m minus 2 operations, or 2n minus 2 operations. And therefore, we end up using 3n minus 3 operations in total, which is totally fine. So here we have 2n plus 1 operations left, but it doesn't really matter. Yeah, we end up using 3n minus 3 operations in total, which is totally fine. And of course, to make this work, we just like do the operation and give all of these s over n. Because s over n is the only value that where all elements can be equal. Okay. Can do a few harder problems now. This is E. E is cool. I like the idea of it. Although I have seen it before, I haven't seen this exact problem before. I've seen a similar like idea being used in a different problem, so it made it kind of easier for me. But I still think it's a cool idea, and I like the idea itself. So I'm kind of a fan of the problem. Okay, let's assume we're working with numbers with 3 bits, because just for the example. All numbers have up to like 30 bits because 10 to the 9th, but it doesn't really matter. So let's say we have the array like 1, 3, 2, 7, 0, 6. That works. Okay. Now, thinking about things in binary is key here. Because let's say 2 numbers have different. Let's focus on 1 bit and say two numbers have different values in these bits. For example, the most significant bit, this has a value of that 0, but this has that value be 1. And so if we XOR both of these bits by either 0 or 1, no matter what, they're still going to be different. Because if XOR is 0, then it leaves the bits the same, and if it's 1, then it flips both of them. So this becomes 1 and 0. But no matter what, if they're initially different, they're always going to be different. And so this is key, because for each element, we're interested in, like, consider some pair of elements, 7 and 2. And then we write these out and we get 0, 1, 0, and 1, 1, 1. We're only interested in the first, like the most significant bit where they differ, because this number is 2 to the 2, which is automatically greater than all other like values of 2 to the k that follow it. For example, this sums to 2 to the 2 minus 1, and that's going to stay true. So if this bit is different, it doesn't matter what the rest of these values are, because the value of this bit uniquely determines whether this is greater than this or not, or the same. So with that in mind, now for each pair of elements, what we want to do is we want to first find the most significant bit where they differ, and then 2, compare them with that bit. So now let's write all these numbers out in binary, which should be quick because there's only 3 numbers, or I mean 3 bits. 000 and 110. Now, all of the values that have 0 in this bit are going to differ with all of the values that have 1 in this bit. Which means that for any pair of numbers where one has 0 and the other has 1, we automatically know the number of inversions. So we can solve for this bit kind of in linear time. What we do is we just, any inversion is going to be a pair where we have 1, 0. So we can go through the array and kind of do like dynamic programming where like dp of I is the number of ones at positions where they're like before I. So number of ones in, say, the prefix of I. And then when we come across a 0, we know that we form an inversion with all numbers that are in the prefix of I. That is, they come before I. And so we add dp of I to like our counter. And dp of I is simple. Every time we encounter a 1, we just kind of increment it. So that part's simple. But every time we add a 0, we know it forms an inversion with only the ones that come before it. So that's how we can count inversions in linear time. And however, it only works for those where they differ in these bits. We don't know the inversions for the ones that have a 0 in this bit, like the pairs where both of them have a 0 or the pairs where both of them have a 1. But these are kind of independent of each other. So the strategy now is to take all the numbers that have a 0 in this bit. And then we can take all the numbers that have a 1 in this bit, and we can solve them separately. Because, keep that red. We can solve them separately, because we know that we're not going to have any, we already know the outcome between any two pairs, any two numbers that differ in that bit. So now we only care about the numbers that have the same in that bit. So we take all the elements that have 0 in this bit, and we take all the elements that we have 1 in this bit, and we solve those separately. So now we have these numbers 1, 3, 2, 0, and we have these numbers 7, 6. So now we can focus on the next bit, which is this one. And we can do the same thing. We can solve for any numbers that have 0 in this bit and 1 in this bit between groups. So for example, I write these out. So this is 0, 0, 1, 1, 0. And this is 1, 1. And of course, they like keep their original order because we just make it that way. So now we have another 1D problem that we can solve in the exact same way. And so on. So each bit ends up being separate, and we can solve for each bit of x separately. But how do we know whether we want to actually change the bit in x or not? Well, in addition to computing the normal amount of inversions, if we change the bit of x, then every single one of these bits is going to be switched. So we also, at the same time, we also simultaneously solve for the number of inversions where every bit is switched. And when we construct x, we take the one that minimizes the number of inversions in their respective arrays. And so here, this is the second most significant bit. So for example, if we do flip it, if we don't flip it, then we have two inversions, this and this. So no flip is 2. And if we do flip it, then we have the array 1001. And it turns out we have the same number of inversions, just these two. So we have 2 inversions in that case too. For here, we have 0 inversions no matter what. So now, while these are separate, ultimately they're both still part of the array. So to get the final cost for not flipping the bit, we sum up all the values of the inversions for not flipping the bit into one final sum. And then the same thing for flipping the bit, we sum all of them over the times we solve for that bit. And then when we decide our final value of x, we take the one that minimizes it. And if they're the same, since the problem wants the minimum, we just we don't flip it, because that will mean that that bit in x is 0 and this bit in x is 1. So if they're equal, so if it's less than or equal, then we don't flip, essentially. And once again, here we have some values that are the same. And so we solve once again recursively for for values in these bits. And then here we have 1, 0, and we do the same thing over here. We have 2 with 0, 2 with 1. We solve recursively for both of those. So the tree of like solving is kind of like we have 0, and then we have 1, and then this expands to 0, 0, and 0, 1. And we're solving for all values that kind of have this prefix in their binary representation. Because all numbers that have this prefix are going to depend on the later bits, and any pairs between numbers that have different prefixes are going to be determined by something in that prefix. For example, these two bits are going to be different. So that is kind of how it works, and then we solve for 000 and 001, and we just continue going. I think you get the idea. But yeah, and I mean, same here. So it's kind of like a cool recursive process, because it's a very like common idea in bitwise stuff that like generally the most significant bit is the only one that matters because it kind of overshadows all of the other bits. That's like a cool property of binary, and it's generally how digits work too. Okay, that's that. So now we'll finish off with F. F is weird, kind of. It's at the same time kind of like something you would expect to be well known, and it probably is, but I'm not sure if it has any well-known approaches because I definitely didn't, like I don't know many well-known things, so I'm not sure. And so the editorial has a very cool solution that's like, it kind of involves, you basically turn component queries into segment tree queries by like building some virtual, not a virtual tree, but like, it's like an Euler-Tor tree or something, and then you just do stuff with it. I'm not going to describe that one because that's not what I came up with. What I'm going to instead describe is something that shouldn't have passed system tests, but it did. And the complexity is O of n times log squared of n. This is a solution I came up with and passed with during the contest. The official intended solution is O of n log n, and these bounds actually are very tight. I had to resubmit multiple times just to make it so it could pass because n is 2 times 10 to the 5th, and you have 1.5 seconds, so it's not the best in terms of constant. And there's a tiny bit of optimization you'll probably have to do, and even then it'll still be close. But this is kind of a cool solution I found that uses like many properties of DSU, and it does pass. Like I did pass with it, so I think it's still valid to describe. And therefore I'm going to. If you want to see the other solution, a lot of the idea is the same, it's just the final part. So this strategy is split into 2 phases. Let me yoink the sample. So we have 5 vertices, and they're split into components like this and like this. And this is like 1, 2, and 3, and this is 4 and 5. And these edges have indices of 1, 2, and 3, and 4. Now what we're going to do is, well, let's describe like what we want to do first. Let's say we get a query to remove an edge. Then what we want to know is, does this split the graph into multiple components? Because if it doesn't, then we don't really have to change the answer. What we can do is we can store a set of values for each component that basically says like, I'm just going to assume, okay, we're gonna say blue is the array value, like the permutation, and red is the index itself. So basically, at all times, to answer the queries, we're going to maintain for each component a set of value. Actually, I'll make that blue. A set of values that are in each of those components. So this component has the values 1, 2, and 5. And this component has the values 3 and 4. And then when we query for a node, we just remove a value from this component, and then we can print it, as long as we have these sets along the way. And when we kill a component, like when we split a component into two, for example, say I remove this edge, now this set has to be destroyed because there are two different components now, and we make two new sets for each of those components. Okay, now that is going to take too long, because if we have a linked list or something, then if we keep removing things from the edges, it's going to make it n squared. Or like a bamboo tree, however you want to say it. So that's bad. We don't want that. But what we can instead do is we can use the principles of small to large. Let's say I have this huge set, like 1, 2, 3, 4, 5, 6. And then I break things into two components where all of these 5 values remain in the same component, and this value goes to a different one. Then there's no reason to destroy this whole set because these values still remain the same. Instead, what we can do is we can remove this, and then we can make a new set for specifically that one, or specifically those values that are removed from the component. And then if we always make sure we remove the component with the smaller number of numbers, then every time we remove a value from a component and move it into a different one, or every time we erase a value from a set, that implies that the size of its set decreases by at least half, because we always take from the smaller one. So a number can only decrease by at least half, like at most O of log n times, and that means that every value is switched from one set to another O of log n times. So the total complexity is O of n log n. Like we move each element from one set to another O of n log n times, and then we multiply that by like the time it takes for us to move an element from a set. This is generally O of log n. I think we can make it slightly faster, but yeah, I think there's a way we can do like 2 pointers or something for every component. And then when we remove an element, we just kind of like mark it as dead and don't ever think of it again. And so when we move the pointer across, we skip it. That's possible because we only have deletions from sets. So I think there's a way to make this O of 1. It's kind of not the best to implement, but there's a way to make it O of 1. So this solution could possibly maybe be actually n log n. I haven't really thought too much about making that work, so maybe it doesn't actually work, but there's a possibility this can be n log n. If you've understood so far, I challenge you to find that, and then maybe tell me if it actually works out, because that'd be cool. But anyway, T of n is the time it takes to manage the set, either removing or inserting elements. And so that's where the n log squared n comes from. Basically just moving things between the sets. And it's the same argument for the complexity as, for example, small to large DSU. Every time we remove an element, it decreases by at least half. So, but like that's like the reverse of small to large, so it's the same argument. Yeah, there are a lot of ways to think about that. But anyway, none of this is possible if we don't know which element is smaller. I'm going to get rid of all this because it was before. None of this is possible if we don't know. Well, first of all, when we remove an edge, we don't even know if it breaks things into two components. And there's no like how do we check that, right? And similarly, we also don't know which component's going to be smaller if it even does break it into components. However, we can exploit the fact that these queries are offline. And what we can actually do is we can do the queries backwards. So initially, let's make a new graph where we're going to go backwards. And it's kind of like this, and all the elements are still the same. Right, okay. So any edge, like some of these edges are going to be removed by some query, and some of them aren't. So the ones that aren't removed, we're automatically going to have them at the end. So we have to kind of like store a flag for each edge is ever removed in a query, and if so, we don't start off with it when we start going backwards. But the ones that aren't, we do. So for example, in this sample, we remove the edge from, we remove edge 1 and we remove edge 3, which means that the remaining two edges, this one and this one, are there all the time. So we automatically have these two components. And now what we want to find out is what happens after every query edge. And the way to do this is with DSU, which is cool because it's kind of like we applied the principle of DSU to find out the complexity of the hardest part of the solution, and now we can use DSU to figure out the rest of it. So what happens here? We process the queries backwards because the edges are removed in that order. So if we go backwards, the edges will be added in backwards order. So in this example, first, this edge is removed before this one. So going backwards, this edge will be added before this edge will be added before this one. So let's add this edge. Okay. Now using DSU, we can find if these two vertices are in the same component before we merge them. And so first we store for each query if the edge it removes splits things into two components. Because if it doesn't, we don't have to do anything. All the components remain the same. But if it does, then we also need more information. We need to store which component was smaller. And then once we do that, we know when we do a query which elements of the set we want to remove, and we can kind of like get rid of the other ones. So we can, in the DSU, we can do, for example, small to large DSU, or union by size, and then we'll just have the sizes ready. So for this query, we'll check the DSU for these components, and we'll see which one's smaller, then we just keep track of that. If they're both the same, it doesn't matter. So this whole process going backwards to the queries is O of n log n, or sorry, yeah, it is O of n log n because we only do O of n merges at once. Or we do O of n merges in total, and each merge is at most log n, or amortized O of log n, which is the same thing. So it's O of n log n to store the information of, does it break things into components, and if so, which component is smaller? Then once we get all this information, we can now go forward through the queries and do the original strategy. That if we store a set for each component, and we can also store like an identifier, like these are all in component 1, and these are all in component 2. And then when we remove this edge, all the components stay the same, so nothing matters. But when we remove this edge, now we break things into two components. So like small to large DSU, we can manually relabel these components, or we can manually relabel the nodes in the smaller component to be of a different one, say for example 3. And we can remove this from its set and then add a special one for 3 that has that one. And then to answer a query, we just get the set of the component, and if there's no elements in that set, then it's 0, because everything will be set to 0, and otherwise we just take that value. So yeah, that is the solution for it. I enjoyed coming up with this. I also think it wasn't intended to pass. I think the official solution also uses some form of DSU to find information about components, but then it does something cooler. Like it makes a tree out of it, and then you can use pre-order traversal or something to make a segment tree on it. I haven't really thought about the details, so I'm not going to try to describe it, but it's cool. Anyway, those are all the solutions I have. I did not solve div 2 E or F, but this is all of the div 1 E or F, but these are all the problems that showed up in div 2, so hopefully that should be enough. And yeah, okay. Tomorrow I'm going to stream, and it's going to be cool, and we're going to do some contests, and you should check out we go to my channel, you can go to this tab called the Community tab. It's like the fourth one. And then you can vote for the contests you want to see here. And then I'm probably going to have time to do multiple, so I'm going to do them in the order that you vote for them. So for example, here I would do Kickstart F and then round 674, the upcoming Div 3, because for me it's at 4 a.m. Yeah, 4 a.m., so there's no way I'm going to do that live. And I would do the @Coder Beginner Contest third. And then there are these extras because I can't actually edit this. Like, all I can do is delete it. But I can edit this comment, so I can say that, for example, if something comes up, I can say that this extra means that you can vote for this contest instead of the other ones. So that's basically my idea of what's going on here. So vote for the contest you want to see most, and we'll take it from there. Okay, goodbye.